Somebody said Dr. Webb just before we started had a question. What was that?
No, I said there was. Oh, well, never mind. It's about the exam, but yeah.
Well, go ahead and ask. I know I haven't seen the exam.
There was a question on there that just did not seem like. It seemed like it was written a little bit off, and when I asked the TA, she noticed it too. But she's like, just go with what you know, and then mention stuff to it later.
Okay, can you tell me what the question was about?
It's the one talking about which one of these. It's all about the physics, chemistry, physical science, and all that. Mm-hmm. It said, yeah, it was weird. It says which one of these is the fundamental, basically it's like the basic that helps with all the rest of them. Psychology was in there, and I'm like, wait. Physics, does that build on psychology? Like what?
Psychology is not the fundamental science. It's physics.
Oh no, I know. Okay. But it said which one is a fundamental for all of these. So then I was like, how does physics build on psychology? Like that is not like the core of it. And then I think I even asked the TA, does he meaning which one of these is not a fundamental thing of
no, the answer to that one should have been physics.
Yeah, I answered physics because she told me to go with what I know, but the question was worded really badly.
That was, well, I'm pretty sure that was from the textbook. Psychology is, they call it a science because they use the scientific method. Scientists have a hard time with that because it has the problem of you can't really have all the controls that you need for scientific evaluation for the testing part. They certainly try to, but there's just certain things you can't do. Way off topic, but I read an article about a person who took twins who were being put up for adoption and intentionally separated them and then did a study on them without them knowing they were twins. And that to me just seems really unethical, right? But that's why science has a problem with psychology being called behavioral science. But that's why it was included.
That's what I was confused on.
Yeah, it's not a physical science no matter how you cut it.
Okay.
Okay. You had a lab experience on Thursday. How did that go?
Good.
How many dice did you have? Okay, I thought I'd left you 25 and there are only 24 now. That's why I asked the question. Okay, so it was only 24. We're going to now talk about the radioactive decay and hopefully you have just a little better understanding about the way we do calculations with it. Obviously, that lab doesn't tell you really what's going on with radioactive decay. And I started talking about that on Wednesday, so let's continue on. So radioactivity is the result of having an unstable nucleus. I talked about that. And when you have radioactive decay, you're going to have something that's emitted because you have energy going out. It's existed for a long time and occurs only with the unstable nuclei. And I'm guessing there's a way on that chart to know which ones are radioactive and which ones are not. But I don't know offhand what it would be. So most of the radiation that we actually encounter in daily life, because we are constantly getting radiated. I mentioned the radiation with neutrinos on Wednesday. Nobody worries about the neutrino radiation for a very good reason. The neutrinos don't interact with us. We don't worry about light radiation generally, right? There is light hitting you right now. That's radiation. It's not nuclear radiation, but it's a type of radiation as well. Nobody worries about it because it's not going to damage you. We worry about the kind of radiation that can damage you. So the kind of radiation that can damage you, well, surprisingly enough, probably the radioactivity of your own body, some of that is the kind of radioactivity that can damage you. Each one of you is radioactive. One of my professors in graduate school, he was old and very cynical. He was telling me, he was our nuclear safety officer on campus. He was telling me if I were to take all of the radioactive atoms in your body and compress them into a little cube that's 1 centimeter on a side, I couldn't give you that cube because it'd be too radioactive. It'd be considered dangerous. Right? How many of you knew that you were radioactive? Okay, just one student knew that you're radioactive. You drink milk, that's radioactive. You eat a banana, that's radioactive. We don't worry about that because the amount of radiation they're giving off is very small. And furthermore, we simply cannot avoid it. But we do worry about situations where there's higher radiation given off. So if you have high energy particles, we worry about it more. If you have high frequency electromagnetic radiation, gamma rays are what we call the high frequency electromagnetic waves that come from the nucleus of an atom. We worry about that a lot. We also worry about the sun's ultraviolet radiation. That's not nuclear radiation. It's not coming from the nucleus of an atom. It's coming from atoms that are just really hot and giving off electromagnetic waves because they're hot. That whole incandescence thing. Remember when I heated up the little ball to show thermal expansion, I got it so it was red hot. It was hot enough that you could see light coming off of it. And then I had the lamp, and I heated that lamp up, and it glowed orange, got hotter, and it moved into white. And you saw the colors. Initially, you had no blue that you could see when it was orange. But by the time it was white, you could see a lot of blue and violet. Well, if you make things even hotter, they're going to give off ultraviolet radiation. You get it hot enough, like the sun, and you have some ultraviolet radiation that has a high enough frequency that it can damage you. And so that's your concern with sun tanning. The ultraviolet at the high end of the range can actually damage your skin, causing skin cancers. So I won't point any fingers because it's not nice, but if you look around, you'll see at least one faculty member who is currently having procedures because of skin cancer on his face from sun radiation. Okay. When an atom decays, when it undergoes radioactive decay, what's going on? Now, this is not something that I have given you the answer. This is what I want you to give your best understanding. Your best understanding, when an atom undergoes radioactive decay, it I'm guessing, Ivy, did you have to hit enter?
It was an accident, yeah.
Okay, yeah, you put in the ones you believe to be true and hit enter.
The ones? Oh, wait, what?
I think, is it only one or is it more than one? That's what I was asking. Did you have to hit enter or was it just a...
Pressed one without
okay.
And it went.
Okay, then you only pressed one, okay.
Yeah.
Since we haven't discussed this...
Can I change mine?
Yes, you can.
Okay.
It takes the last, I mean, I can set it so you can't, but I want people to be able to just sit, think about it, and answer what they think is right. Okay. All right. And I did not change the color scheme, so, and my new plan didn't work. Heck yeah. 0, 1, 2, and that's 3, so it must have been 4 because we had 7 answers. So there's the answers we had. Now, because this wasn't something that you've been lecturing, I'm not even going to ask you to discuss amongst yourselves or to justify your answers, but just go to this. When an atom undergoes radioactive decay, what I have told you is that the nucleus was in an unstable configuration, and it falls to a lower energy, more stable configuration. That's what I told you, and I've told you that because it dropped to lower energy, something has to come out with energy. Now that something could be different things. So, becomes an ion of the same element. What does ion mean? Has a charge. So the number of protons in the nucleus doesn't equal the number of electrons orbiting the nucleus. That's what it means to be an ion. What does it mean if it's the same element? Did you answer, Ivy? I did not hear you. It sounded like you didn't.
I was saying it needs to have the
same. Okay, same number of protons in the nucleus. Now remember, a radioactive decay is a change in the nucleus. It's not a change in the electrons orbiting the nucleus. If you have the number of protons in the nucleus change, it would become an ion, but it wouldn't have the same number of protons. If you don't have the number of protons change, it's not going to become an ion. So that one can't be correct because you would have to change element if it becomes an ion. So everyone was correct that that was not the answer. Now the next one, it becomes an isotope of the same element. What does the word isotope mean? Same number of, remember I made a big deal of the spelling?
Oh, protons.
Same number of protons, but different neutrons. Well, if I have a nucleus that kicks off a neutron, will it have the same number of protons? Let's say I have a carbon-14. Carbon-14 has 6 protons and 8 neutrons. If it kicks off a neutron, which is not what happens, by the way, but if it kicks off a neutron, how many protons will it have? Starts with 6, gets rid of the neutron, how many protons remain? 6 still. So it's the same element. But the number of neutrons, we start at 8, it goes to 7. How many neutrons remain? Well, 7. So it's a different number of neutrons. It's a different isotope. The same protons, different neutrons. So if carbon-14 decayed that way, it would be an example of this. So this is a correct option. So that person gave a correct answer. Now the next one turns into a completely different element. Well, something else we could do to change the nucleus would be to kick off a proton. If it kicks off a proton, it's a completely different element. If a carbon kicks off a proton, it would become a boron. So that's another correct option. And finally, may or may not turn into a completely different element. Well, since it turned into a completely different element in C and it did not turn into a completely different element in B, that one was also a correct option. So everyone answered a correct option. Right? These are different things that can happen with radioactive decay. So let's go back to the days of the Curie family. The Curie family, which is one of the ultimate scientific families. Dad got a Nobel Prize. Mom got a Nobel Prize. One of the kids got a Nobel Prize. They had 2 kids. How'd you like to be the last person in the family without a Nobel Prize? Oh. Harsh, huh? So Marie Curie and her husband, Pierre, they were studying radioactive decay. Curium is named after Marie Curie. Also, polonium, named after her homeland of Poland, is named for her. So Marie Curie and Pierre are studying this, and they noticed that there are different types of radiation. And so initially, they didn't know what the types were, and so they just judged them by how penetrating they are, how easy it was to shield them. So they found one type of particle that was really easy to block. Like if I was worried about that kind of radiation, I could just hold this paper up and it would completely protect me from that radiation. They called the one that was really easy to shield alpha. So alpha, this is just the Greek alphabet, alpha, you know how it works, was the easiest one to shield from. Then there was another type of radiation that was harder to shield. If I wanted to shield myself from that, I'd have to give myself something like this piece of aluminum plate. It would probably shield me pretty good from the next type that they called beta. So beta, you need a reasonable shield to protect you. The last one, gamma, gamma would go through this. You need like a lot of lead to protect you from the last one, from gamma. Gamma is the 3rd letter of the alphabet. Alpha and beta are the 1st and 2nd. That's what we call alphabet. So these are labeled by how easy it is to shield. Alpha is the easiest to shield, beta is the middle, and gamma is very hard to shield. Now, the shielding, protecting yourself from the radiation is really important because how did Marie Curie die? She died as a result of all the radiation she received in her research. Unlike her husband, who, if I remember right, was out in the street, fell down or got knocked over, and a wagon ran over his head and crushed his head. Yeah, not a great way to go. Reminds me of a dumb joke with the whole funeral thing. But let's move on and not talk about dumb, macabre jokes. So we have these types of radiation. Now, scientific method. You had a scientific method problem, right? The last one of the test. And you had to go through, and the first step was observe something interesting. Well, they observed that you had these particles, and then they did some more tests just to see what's going on. And so one idea they had was, well, let's see how they respond in a magnetic field. So they put them in a magnetic field, and they found the alpha particles were deflected one direction when they went through the magnetic field. The beta particles were deflected the other direction, and the gamma particles weren't deflected at all. That would be curious. That leads us to the observe something interesting. Part 2 is then come up with a hypothesis that explains why this happened. It's based on scientific ideas and makes testable predictions. Well, we know that if you have a charged particle that has a positive or negative charge going through a magnetic field, then it's going to have a force that makes it deflect. And that force's direction will depend on if it's a positive charge or a negative charge. And so a quick hypothesis is because we know a charged particle will deflect in different directions depending on the charge, we must have that the alpha particles have one type of charge, positive, and the beta particles have the other type of charge, negative. And so then lots of experiments were done to test this, and sure enough, they determined that the alpha particles have a charge of +2. If I say +2, I mean that it has a positive charge with 2 more protons than electrons. So it carries a positive, a +2 charge. And the beta particles carry a -1 charge. That means they have 1 more electron than proton. And the gamma particles carry no charge. Now I'm going to go further with further study looking at ways to analyze what the mass is. We also know that an electric field, right? We didn't study magnetic fields and electric fields. But if you put a charged particle in an electric field, it'll also put a force on it. And you can actually adjust the electric and magnetic fields to determine what the charge to mass ratio is. And eventually they determined that the alpha particles are 2 protons and 2 neutrons. So 2 protons and 2 neutrons. If we look at the periodic table, which element has 2 protons? Helium. Helium is the second one. It has 2 protons. You can tell, look at the top right-hand corner. If you look at the atomic mass of helium, I'll just let you read it. What is the atomic mass of helium? 4. So if it has 2 protons, an atomic mass of 4, how many neutrons does it have? 2. So helium is 2 protons and 2 neutrons. So what is this alpha particle? It's a helium nucleus. It's not a helium atom because it has no electrons around it. But it's a helium nucleus. Where does it come from? It comes from the original nucleus of the atom. So let's say that you had a uranium-235. Uranium-235 is going to decay, giving off an alpha particle. So let's just write this down as a math equation. Uranium-235. That 235 is the atomic mass. And what does the atomic mass mean? It's the number of blank plus blank. Z is the symbol for the number of protons, the atomic number. N is the symbol for the number of neutrons. So it's the number of protons plus number of neutrons. Down here, we usually put the atomic mass. So for uranium, the number of protons is 92, right? I can't see it from here, so I'm kind of trusting memory. Tell me, you're looking at it, Leslie, am I right?
Like the mass?
The atomic number of uranium, is it 92? Yes. Yeah. There are a couple different common isotopes of uranium. Uranium-235 and uranium-238 are the two common isotopes of uranium. And uranium-238 is like 95 or maybe it's 99. It's a huge percentage of the uranium. So this is the minority portion of uranium. It's the stuff they make bombs out of, the isotope uranium-235. So if that's going to decay, it gives off an alpha particle. How many protons are in the alpha particle? 2. And what's the total atomic mass of the alpha particle? Protons plus neutrons? 4. So there's my nucleus gives off this alpha particle. What's remaining? How many protons are remaining in the nucleus? It's 90 because I had 92. I take away 2, and I have 90 left. What's the total mass remaining? If I had 235, take away 4, 231. So we can look back there and say, what is 90? So I find my uranium, go 2 to the left, and I see it's thorium. Thorium has 90 protons. So that would be my reaction. There is one additional thing that we often forget. The number of electrons didn't change the instant it decayed. So at this moment, it's going to have a -2 charge because it's going to have 92 electrons and 90 protons. But you know what's going to happen real quick? Those 2 electrons are going to say, I am not needed here. I am not wanted here. And they're going to take off. But that would be the process of an alpha decay. So you had a chunk of the nucleus broke off. Why is this alpha so common? Well, that goes back to Maria Geppert-Meyer's theory. Her theory, of course, was based on observation. You know, the theory doesn't predict this so much as this guided her in the theory, that 2 protons must be a stable configuration. You must have a shell that's complete if you have 2 protons in it. And 2 neutrons must be a stable configuration, complete with 2 neutrons, and having the 2 protons, 2 neutrons is together, apparently some kind of stable shell. And so this is a very stable nucleus, 2 protons, 2 neutrons, and so that piece breaks away as one chunk. So that's the equation for an alpha decay. Now, if we go to the beta decay is much more confusing. So let's say that I have a nitrogen so nitrogen doesn't decay this way. I'm trying to think of what decays with beta decay, and of course I don't have any on the top of my head. I probably have one coming up. I'm just going to put X, not standing for any specific element, but just saying I have an element X. And let's say that it has, okay, if I say 37, then you can determine what element should this be. Of course, I can't tell from here. I'm trusting you guys can read. It's what? Lithium? Rubidium, okay. So that would be, I totally can't see anything, RB. And just for grins, what is the red number there, the atomic mass for rubidium, that just its average? It's how much? 85. Now, I have not looked this up, so don't take this as a reaction that actually occurs. If it's going to undergo beta decay, it has an electron coming out of the nucleus. Anybody see a problem with that statement? Because you should. An electron coming out of the nucleus. Yeah, electrons aren't in the nucleus. Now, when I was in high school physics and we learned about this, I thought, well, as we go through this, it was really clear to me that a neutron is just a proton bound to an electron. Au contraire. You actually are creating this electron through a particle interaction. It wasn't there, it's created in the decay. But for simplistic thinking, we can think of as a neutron as a proton and electron bound together. Not at all what it is. But what happens is the number of protons drops, or excuse me. Yeah, the number of protons is going to be one more, so it's like it took away a negative proton. And the number of total things in the nucleus stay the same. Oops, 0. So it has no protons and no neutrons, but because it's taking away an electron, it's actually going to make it so you have one more proton. One neutron is converted to a proton in this process. So now I'd be left with how many protons? 37 equals minus 1 plus. What minus 1 is equal to 37? 38. And 0 plus what is equal to 85? And so if this occurred, my rubidium would become strontium. Now, strontium, rubidium, there is a reaction where one decays into the other, but I don't remember which way it is. I guess I could have used, potassium argon is definitely the wrong way. But this would be a potential type of beta decay. You have essentially a neutron here became an electron plus a proton. So the number of protons went up by 1. The number of neutrons actually went down by 1 in the beta decay. Now, like I said, there's no electrons in the nucleus, and a neutron is not a proton bound to an electron at all. A proton, if you look at that fundamental particles and interactions, you actually can see what a proton is made up of. As we understand things, a proton is an up, up, down. It has 3 quarks in it, 2 ups and a down. A neutron is an up, down, down. Once again, 3 quarks, but it's converted 1 up into a down. That process of converting up into a down had to release energy, and that energy produced actually the electron that came flying out, plus it has to produce another type of thing that I've already mentioned, plus what we call a neutrino. That's the neutrino. It's an electron neutrino. That's what the subscript E is. Now, there's a lot of complicated physics that goes on with this, but anytime you have a beta decay that produces an electron, it also produces that antineutrino. So that's what the beta decay is. It's more complicated than the alpha decay because you have a complicated particle physics interaction going on that is destroying a neutron and creating a proton and an electron antineutrino. Question?
Is that what you mean by an electron in a way is made or produced or whatever you said before? Like the neutrino, or I didn't really understand that part before. So you said something that the beta is different because you said something about an electron.
Okay, so a beta particle is an electron that comes from the nucleus that has no electrons in it. So that's, kind of like saying, I'm going to withdraw $10 from my bank account that has no money in it. Right? You can't do that. And so what is going on is is that a particle is being destroyed. The neutron, in this case, is being destroyed. And in its place are created a proton, an electron, and the electron antineutrino.
So a neutron is being destroyed.
Yeah.
Okay.
And if you want to get more complicated, it's a down has to interact with something else to be annihilated and to create an up and these things. Right, those are the quark interactions. And you don't need to know anything about the quark interactions at all. You do need to know that the beta decay has a neutron converted into a proton plus an electron in that neutrino. So that's our beta decay. Now the last one is the easy one. Let's say we have, what is, I think americium is a gamma emitter. I didn't look up what emits what. Quit that while I'm at it. But if for a gamma decay is an electromagnetic wave. It's like light. What's the charge of a particle of light? We've never talked about it with the charge, have we? Because light has no charge. And so there's no charge to it. What's the mass for a particle of light? Doesn't have a mass either. So what do we have? We just have a particle with energy, but no mass, no charge. Now, surprisingly, it does carry momentum. If it hits you, it'll put a force on you. The light does put a force on you, surprisingly enough. But it has no mass and no charge. So the gamma decay is really simple. XZN produces XZN plus gamma. Sometimes we'll put like a star here to say that was an excited state for the nucleus and gets rid of that star by saying now it's in a lower energy state. But there's no change fundamentally to the nucleus. That is like taking the nucleus and saying, okay, the nucleus was like this, and now it's fallen over like this, so it has a lower energy state, but it's still exactly the same nucleus. You have the sound come out, you have the gamma particle, the electromagnetic wave, come out, but the nucleus is just more efficient in a lower energy state that has all the pieces there. So a gamma decay does not change the nucleus. It only changes its energy state. So those are the three types.
Wait, what does it change?
It just changes the energy state of the nucleus. It doesn't change the particles that are in the nucleus. You still have the same number of protons, the same number of neutrons. So you didn't change the element at all. It's going to behave exactly the same as it did before. You've just had the nucleus go to a lower energy state. Okay, so that's probably good enough for slide number 2 in the presentation, don't you think? We're 34 minutes into the lecture. Okay, I said number 2. We had the question in between. So here's a quick rundown of the properties of alpha particle, then beta, then gamma. So the alpha particle, 2 protons and 2 neutrons, or a helium nucleus. It loses energy quickly in an interaction. That's why it's easy to stop. Because when the alpha particle hits something, it has a relatively large mass compared to like a beta particle. So it gives off, when it collides with something, it will lose a lot of energy, and so it stops pretty quickly. The next two after that are talking about it stopping. It causes significant damage because it has a lot of energy that's going to be very quickly dissipated. So while alpha particles are very easy to stop, like your skin will stop alpha particles, they'll sweat. But your skin, if it's stopping alpha particles, is going to absorb a lot of energy, which means you have the potential to do a lot of damage by having alpha particles stopped by your skin. Only to your skin. So if you get cancer from alpha particles, it's going to be skin cancer unless you ingest it. If you ingest an alpha particle, then you're going to have, or if you ingest an alpha emitter, something's radioactive, gives off alpha particles, then you're going to have those particles absorbed somewhere in your body by something that's probably going to be more prone to problems than your skin. Skin is the easiest one to to deal with if it's cancerous. It's also the easiest one to see where the cancer forms. The alpha particle, once it leaves the nucleus, it's screaming out here with 2 protons and no electrons. It really, really wants to have 2 electrons. It's a noble gas. Helium's a noble gas. It loves its 2 electrons. So it's going to very quickly pick up electrons from things it passes to become a neutral helium nucleus. And as we saw, it's deflected by electric and magnetic fields. That's what told us about its charge. Okay, so going to the beta. The beta is an electron that comes from the nucleus. It has a smaller mass and smaller charge than alpha. It loses energy at a slower rate than the alphas because it has a lower mass. And thus it's going to penetrate more because it loses it more slowly. It's still an electron. So once it's slowed down enough, it's just going to be an ordinary electron. So what's the difference in a beta particle and an ordinary electron? The beta particle is really high energy because it came from the nucleus. When it loses that energy, you're not going to call it a beta anymore. You're just going to say it's an electron. It's deflected in the opposite direction as the alpha particle in presence of electric and magnetic, meaning that it had the negative charge. And then the gammas, high-frequency electromagnetic radiation produced from the nucleus going to a lower energy state, no change in the nucleus number of protons and neutrons. It's the most harmful because it is the most penetrating of the radiation. They're pure energy, not affected by electric fields and magnetic fields. Now, very quickly, Loma Linda, back when I was in college, okay, you don't know the part about back when I was in college, but you probably know the other part. They were the first medical facility in the nation, actually I think in the world, to build a particle accelerator to accelerate protons to be used in medical treatment. And today, if a man gets prostate cancer, which eventually we all will if we live long enough, one of your options for treatment is to go there and have them bombard your prostate with protons. Have you guys heard about proton treatment facility there at Loma Linda? Nope. Wow, because we're really proud of it. That's groundbreaking medical technology there at Loma Linda. It was, of course, funded by the federal government. The federal government funded 2 facilities doing it at that time. The other one decided it wasn't worth their money. Now there's lots of facilities because Loma Linda has shown that it's very effective. Why proton treatment? What is the goal of cancer treatment? Very simple goal. What is the goal? Okay, to eliminate cancer cells, to kill cancer cells. We want to kill them. And so how do we kill them? Well, we have a couple different options. We have a couple teachers on campus that are going through different procedures. I talked about one with skin cancer, there's one with brain cancer, one with colon cancer. We've got a lot of cancer rolling around right now. Pray for us, teachers. So options. What is the first thing that you think of for treatment for cancer? Chemo. Okay? Chemotherapy. Now, there is a first step that usually comes before chemo. That's a surgery to cut out what you can. Cut out the bad stuff and then try to kill what you couldn't cut out. For prostate, they use, if you're doing the radiation, they actually don't do the surgery. They just go straight to the other procedure. Chemo. Chemo is taking a chemical to kill the cancer cells. By definition, you're taking a poison when you take chemotherapy. It's supposed to be a poison. It's not supposed to be a health food. So you have to think about this. You're taking something that is damaging to your body, that's going to kill cells because you're hoping to kill the cancer cells. So the poison they give you is going to be something that is more likely to kill the cancer cells than to kill normal cells. They target things like fast reproducing cells. Unfortunately, your hair follicles are fast reproducing, so it causes hair loss very often. But you're taking a poison trying to kill it. My wife gets really outraged. Why would you take a poison? And it's because it's a last-ditch effort. It's not like, hey, this is healthy, I'm going to take poison. Nobody says, most people don't say that today, right? It used to be, oh, you're looking a little little robust. You should take some arsenic to get some white powder in your skin. They had different medical ideas back then. So you're taking poison to try to kill the cells. Another one that you may have heard of is radiation treatment. And one form of radiation treatment is high-speed electrons. That was very popular when I was in college. I did a tour of Loma Linda's medical physics area when I was in college. And they showed us all these little particle accelerators that accelerate electrons, and then they pound them into people. Why? Because they have this energy that will then be absorbed by the body. And if you can get the energy absorbed by the tumor, you'll cause a lot of damage to the tumor, killing a lot of it. Electrons are more penetrating than alpha particles, right? The more mass, the less penetrating it's going to be. Why do they now use protons in their treatment? Because protons have a much bigger mass than electrons. And because of that much bigger mass, the protons have their energy that they deposit is much smaller in the region it's going to be. If you look at the tissue in the body that the particles are going through, for an electron profile, it'll be something like this. So the vertical axis is energy deposited. Deposited per volume. And this is depth. So that's what the curve looks like for electrons. If you use protons with their higher mass, the curve looks something more like this. Well, what do you have? You have a much bigger proportion of the energy that is here at the depth you want. You adjust so you're going to have the right depth. But you have a much bigger proportion of the energy that's deposited in your target area. Less energy deposited in the path there. And so that's why they had the idea of using a proton treatment so that you could have better control of where the energy is deposited, less energy deposited in the healthy tissue, bigger proportion deposited in the cancerous tissue. And so the goal is to put lots of energy in there. That energy is going to break bonds between molecules, and by breaking those bonds, cause them to malfunction and hopefully die. What caused the cancer in the first place? Something broke a bond, caused it to malfunction, and it reformed in an incorrect fashion. That's an option with radiation. It can create cancer. That's why we worry about it. So they're using something that can create cancer to kill cancer, because statistically, radiation is much more likely to kill cells than it is to create mutant cancerous cells. So we're receiving radiation all the time. Almost all of the damage that's done to us by that radiation is simply killing cells. And if you kill them at a slow rate, your body just regenerates them and you go on and you don't even know it. If you kill them at too rapid of a rate, then you can have what we call radiation sickness. So if you are exposed to very high radiation, you might initially just feel a little sick. And a day or two later, your whole body starts to break down and then you die. Because you had so many cells that were killed that your body couldn't regenerate them, and you die. It's one of the dangers of radiation at high dosages. Long-time exposure can produce mutations and cancers. That's the concern with long-time exposure. Okay, strong nuclear force. We have 4 fundamental forces in nature. In the physics section, we talked about 2 of the fundamental forces. We talked about the electromagnetic force, the force between charges, Coulomb's law. We had, opposites attract, likes repel. We talked about gravitational force, the force between 2 objects that have mass. Those are 2 of the 4 fundamental forces. And everything that you and I interact with on a daily basis is one of those 2. The normal force I talked about is just a result of the electromagnetic force holding molecules together. They can't separate, and so it pushes back so I can't go through. Inside the nucleus, at these extremely short distances, there are 2 additional forces. We only know of 4 fundamental forces, so the 2 additional ones are only going to be noticeable if you have things that are really close, like inside the nucleus. And so those two forces are called the strong nuclear force and the weak nuclear force. So the strong force and the weak force, they're both nuclear forces. That's forces that only interact if you're really, really close. And those forces, called strong because they're really, really strong if you have things that are close. So look here, this picture. If I have two protons that are super close, like in the nucleus, the strong force is going to attract them with a very, very strong force. Now, if there are two protons, they're like charges. What kind of force do we have between like charges? They repel. So there's also going to be a strong repulsive force. But if you get close enough, that strong force will become stronger than the repulsive force, and the two protons will stick together. That's what's going on in the nucleus. The protons are sticking together because they have a really, really strong attractive force due to the strong force. They do have a repulsive force because of the electric charge. The strong force only occurs between protons and neutrons. Protons and protons are attracted, neutrons and protons are attracted, neutrons are attracted. So it's like gravity, it's always attractive, but it only happens between protons and neutrons. Now, if I say that and somebody listens to this recording and they know what they're talking about, they'll say, you forgot quarks. Strong force acts between quarks. It does. But we're not talking about quarks at this point, so that's why I said only between protons and neutrons. So that strong force doesn't affect electrons, only protons and neutrons. It holds the nucleus together. The electrostatic force is trying to push protons away from each other. If we make a nucleus that has lots of protons, like uranium with 92 protons, there's a lot of force trying to push it apart. And the electric force is a long-range force, so every proton in the nucleus is trying to push other protons away. The strong nuclear force is a short-range force. Only next-door neighbors are trying to hold together. So if you have uranium with 92 protons, the long-range nature of the electrostatic force actually makes it so there's more force pushing it apart than holding it together. So how does the uranium nucleus stay together then? You chuck in neutrons. Because the neutrons are only going to be attracted by the strong force but not repelled by the electrostatic force. So if you put in more neutrons, it becomes more stable. And that's why with uranium, you have, for instance, 92 protons, but a total mass of 235, which means 147, right? 147, 92 is 235. I think that's right, 147 neutrons. A lot more neutrons than protons because those help spread out the protons and provide more attraction so that it can be somewhat stable. But it is the repulsion caused by all those protons that makes the uranium unstable, makes it radioactive. So that strong, and there's also the weak nuclear force, but we're just going to talk about the strong here, is important for why the nucleus stays together. It's what holds the nucleus together. So our second clicker question and final clicker question, as luck would have it, the strong force is a force in the blank. You're right. It's because I had that problem. Okay, it's open now. I'm sorry. Thank you for telling me instead of waiting until class is over and say, hey. All right, everybody answered 0, 5, 2, and it must be 1. Strong force is a force in the atom that holds electrons in orbit. Because of time, I'm not asking you. Strong force does not affect electrons. Only affects protons and neutrons. What's the term for protons and neutrons combined? Nucleons. Hey, look at that. It's a force in the nucleus that holds nucleons together. So the correct answer was that. Okay, have a great day. I'll see you Wednesday, yes. My siblings